Hello everyone, this is Chandrasekhar welcoming you all once again to this wonderful session of physics where we are going to discuss about a very beautiful concept of Gauss theorem. We can also call it as Gauss law in electrostatics. Before understanding the Gauss law, we need to understand one term that is called as electric flux. Let us try to understand the electric flux first. Denoted by phi, which is also known as flux density. Also call it as flux density. The flux density is a physical quantity which is used to measure the strength of the electric field. Or we can say the physical interpretation of electric flux is the number of electric field lines crossing a given surface or passing through a given surface. That is called as electric flux. For small element area dA, we can say d phi is equal to electric field vector with the dot product of dA vector, or phi can be called as integration of E dot dA vector. So because it is the dot product of two vectors, and which you already know, it is as the dot product is always a scalar quantity, so it is a scalar quantity. It can be positive or it can be negative. It can be zero as well. If electric field and area vector are perpendicular to each other, then the flux will be zero. So the unit of this electric field, you already know the unit of electric field is Newton per coulomb into area will be meter square, or another unit of electric field is equal to volt per meter into meter square. So we can also call it as volt meter is the unit of electric flux. Now what is this dA vector? dA is called as area vector for a small elemental area which is perpendicular to the surface. It is always taken as perpendicular to the surface and outward. The area vector is taken as perpendicular to the surface. For this board, the area vector is taken as normal to the surface and outward. All right. Now, if an electric field you already know, we can find out the dimension of this as well. We can write the dimensional formula as well. Now, if the electric field is uniform, or we can say when the electric field is constant, so for that we can say phi is equal to E dot integration of dA. Phi, E will be taken outside the integration, so we can say phi will be equal to E dot A, dot product, or we can call it as magnitude of E multiplied by the magnitude of area into cos theta. Theta is the angle between E and A. Theta will be the angle between E and A. Now here, if the surface is kept parallel to electric field, if the surface is kept parallel to the field, you can see like this. If the direction of electric field is along x direction and the surface is kept like this, if the surface is kept parallel, so we can say area vector will be perpendicular to the surface and it is making an angle 90 degree with the electric field. So we can say theta will be equal to 90 degree, and if theta is equal to 90 degree, then phi will be equal to 0. You can understand this concept physically as well. What is the electric flux? It is the number of electric field lines crossing a given surface. If the surface is kept parallel to the electric field, no electric field lines will cross the surface. The electric field lines crossing the surface will be 0, isn't it? So phi will be equal to 0. If the surface is kept perpendicular, to the electric field, in that case what will happen? The surface is kept perpendicular. If the direction of electric field is like this, so area vector will be normal and outward. So can we say the angle between E and A in this particular case is 0 degree? If theta is equal to 0 degree, then phi will be equal to EA, isn't it? That is positive. Outgoing flux is taken as positive. And if the situation is like this, electric field is like this, and area vector will be normal and outward. So here it is 180 degree, for theta is equal to 180 degree. Then phi will be equal to minus EA. It is incoming flux. Incoming flux is taken as negative. Incoming flux will be taken as negative. So we can solve number of problems using this relation. If let us say the electric field is given by 2x square I cap, or it is constant electric field, 2I cap plus 3j cap minus k cap, and area vector is given by I cap plus 2j cap plus k cap. Let us say this. What is the flux? That is dot product of electric field vector and area vector. You know how to take the dot product. 2 into 1 will be the first term, plus 3 into 2 will be the second term, plus minus 1 into 1 will be the third term. So it is 6 plus 2, 8 minus 1, 7 volt meter will be the flux. The question can be taken in another way. If the electric field is given, let us say this is the electric field given. If the electric field is given by the expression, and there is a square plate of side 5 meter. Square plate of side 5 meter is kept in xy plane. If it is kept in xy plane 5 meter, then area vector will be equal to 5 into 5 k cap, isn't it? Area vector. If it is kept in xy plane, then the area vector will be 25 k cap. So what is the flux? It is minus 1 into 25, isn't it? So it is minus 25. What does that mean? It is incoming flux. I hope this is clear. Now, if it is a hemisphere, let us say hollow hemisphere, and the direction of electric field is like this. Electric field is constant, uniform electric field, and for the curved surface, if you see, here the area vector will be like this, dA. Here the direction of area vector will be perpendicular, like this. Here the area vector will be like this. Here the area vector will be normal and outward. But we have to take the dot product. So this is, let us say, dA. We need to take cos component of dA. dA cos theta is this. dA cos theta will be this. dA cos theta will be this. dA cos theta. dA cos theta will be this. So if we take the component of dA in the direction of electric field and multiply them, then we will get the total flux. So if we take all the horizontal component of dA and we put them on a horizontal screen, then it will give us the projection of this curved surface on the horizontal screen. So here the area will be the projected area. Why it is the projected area? Because area is not perpendicular to the area, is not in the direction of electric field. So we need to take the component of area in the direction of electric field, that is projected area. It will be area of the circle, pi r square. So we can say for curved surface, when it is the curved surface, we can say pi will be equal to E into projected area. Projected area of the curved surface. So if I ask you for this particular figure, if you ask you what is pi entering, that is equal to E into pi r square, projected area. What is phi leaving? If it is a closed surface, phi leaving will be from this. So phi out is equal to again E into pi r square. It is a flat surface, it is not a curved surface. So phi net is equal to 0 for a closed curve. For a closed curve kept in uniform electric field, phi net will be equal to 0 until and unless there is no charge enclosed by the curved surface. Clear? Now let's see when a point charge is kept, when a point charge is kept at one corner of a rectangular plate. So is point charge Q will develop electric field which is radially outward like this. So here the electric field will become parallel to the surface, and when the electric field will become parallel to the surface, phi will be equal to 0 because no electric field line will cross the surface. When the charge is kept on the surface, flat surface, then it will not develop any flux. There is no flux for this case, right? Now if E is not constant, if it is not uniform electric field, then in that case phi will be integration of E dot dA. We need to go for this. If there is, let's say there is a question, if E is given by x square I cap, electric field is varying in x direction, and there is a cube kept at x is equal to 2, and the side of the cube is 1 meter, then what will be the flux, net flux through the cube? If E is not constant, then for the closed surface flux will not be 0. Look, at x is equal to 2, the flux entering will be equal to, at x is equal to 2, E will be equal to 2 square into area will be equal to 1 into 1, that is equal to 4. Pi out, that is at x is equal to 3, flux will be leaving from this. So it is 3 square is the field into again 1 into 1 will be the area. It is 9. So phi net will be equal to phi out minus phi in. So that is 9 minus 4, that is 5 volt meter. It will be 5 volt meter. Now, if there is a charge Q kept at the center of a sphere of radius r, let us say. So what is the total flux through the sphere? Look, when this is charge is kept at the center, it will generate electric field which is radially outward like this. And the value of electric field at this location, you know, electric field on the surface of the sphere will be equal to K into Q upon R square, isn't it? KQ by R square. And here if you see, the electric field and area are parallel to each other. At this location also, the area vector will be radially outward, electric field is radially outward. Electric field and area vector are parallel to each other at all the points of the sphere. So if we add these area vector, or if we add all the area, it will be the area of the sphere. So phi will be equal to E into, it will be area of the sphere 4 pi R square, and E will be equal to, so phi is equal to E, that is KQ by R square into 4 pi R square. R square getting cancelled out. K is equal to 1 upon 4 pi epsilon naught into Q into 4 pi. This 4 pi will also get cancelled out. Phi is equal to Q upon epsilon naught. Phi will be equal to Q upon epsilon naught. So from here we can define the Gauss law. So this is called as Gauss theorem. We can define the Gauss theorem or Gauss law. Net electric flux through any enclosed surface, any imaginary closed surface. It can be any imaginary enclosed surface. So net flux through any imaginary closed surface is equal to 1 upon epsilon naught times the total charge enclosed by the closed surface. This is, which can be written as integration for the closed curve E dot dA. This. So the net electric flux through an imaginary closed surface is equal to, this imaginary closed surface is called as Gaussian surface, is equal to 1 upon epsilon naught times the total charge enclosed by the surface. This is used to find out the electric field for the symmetrical charge distribution. We will come to that point later on. But can we say, if Q enclosed is equal to 0, then phi net will be also equal to 0. I have already told you that if there is no charge enclosed by the closed surface, then the net flux will be equal to 0. If there is a charge enclosed, then the net flux through the surface will not be 0. So there are some properties of this Gauss theorem. We can discuss one by one. The surface is called as Gaussian surface. It can have any shape or size. So if there is a Q1 charge, this is minus Q2, then there is a Q3, and here that is a, let's say, Q4 minus Q5. This is our Gaussian surface. For the Gaussian surface, the flux does not depend on the location of the charges enclosed by the surface. Whether Q1 is here or here, it does not matter. As long as it is inside the Gaussian surface, then it will contribute. So we can say phi net through this surface is equal to net enclosed charge will be equal to Q1 minus Q2 plus Q3. Q4 and Q5 will not appear. Plus Q3 upon epsilon naught. This is the net flux. It does not depend on the shape and size of the enclosure. Whether the Gaussian surface is like this, as long as the total charge enclosed remains same, then the flux net flux will remain same. When the charge is outside this Gaussian surface, look why it is not contributing to the flux through the Gaussian surface. From this charge will generate electric field which will enter from here and then it will leave from here. So the number of electric field lines entering will be same as the number of electric field lines leaving. So there is no contribution of outside charge in the calculation of flux. I hope that is clear. Now another property is at the surface, for the Gaussian surface, the flux is dependent only on the charge enclosed by the surface, but if we want to calculate the electric field, it depends on the charge enclosed as well as the charge which are outside. The electric field here will depend on the charges which are inside the surface as well as the charge outside the surface. And if E is equal to 0, if there is no electric field, we can say phi will be equal to 0. If electric field, but if phi is equal to 0 may not imply E is equal to 0, isn't it? Phi is equal to 0 may be due to no charge enclosed by the surface. The charges may be outside the surface. So these are some of the properties. Now let us discuss some questions based on this concept. Look, if there is a cube, if there is a cube and if the charge is kept at the center, if there is a charge which is kept at the center of the cube, here there is a charge q. So what is the flux from each face of the cube? Now look, from the symmetry we can say the total phi net will be equal to q upon epsilon naught, and from symmetry we can say from each face of the cube it is 1/6 of q upon epsilon naught, symmetry, because the charge is placed at the center. And if I ask you if the charge is only through the corners, if the flux is only through the corners, what is the net flux from each corner? Because there are 8 corners, so it will be 1/8 into q upon epsilon naught. There is another example. Look, there is a cube. There is a cube and the charge is placed here, Q, on one face of the cube. Then the charge is not enclosed by the cube. What we need to do is to make the enclosure, because Gauss law is applicable only to the enclosure which is enclosing the charge. So to make it enclosure, we need to have another cube, imaginary cube. This is, let us say, imaginary cube. This is imaginary cube. This is the imaginary cube. So this is the enclosure. So we can say phi net will be equal to q upon epsilon naught. And this charge is at the center of the enclosure. It is from symmetry. We can say phi from each cube will be equal to 1/2 q by epsilon naught. I hope this is clear. Now, if the charge is, look, there is a cube. If the charge is kept at one corner of the cube, like this, the charge q is kept at one corner of the cube. So first of all, we need to enclose this charge in an enclosure. To enclose this charge, what we require is we require four cubes, and along with that we require four more cubes. Like this. Total 8 cubes will be required. I hope you understand this. If the charge is at one corner of the cube, we require 3 more cubes, and over that the one more layer of the cube, 4 cubes. So total will be 8. So this will be the enclosure. So phi net will be equal to the charge enclosed upon epsilon naught. So phi from each cube from the symmetry, it will be 1 upon 8 cube by epsilon naught. And if we ask what is the flux from each phase, the phase which is enclosing this charge will not have any flux. I have already told you, because the electric field lines will be parallel to those phases. So 3 phases are not available. So out of 6 phases, only 3 phases are available for this. So phi from each phase will be equal to 1/3 of q upon 8 epsilon naught. 8 epsilon naught. It is q upon 24 epsilon from each phase. Similarly, if I take similar type of example, look like this. There is a charge q1 here, there is a charge q2 here, there is a charge q3 here. Combination of all these 3 cases. So due to q1, phi 1 will be equal to we require 8. So q1 upon 8 epsilon naught. Due to q2, phi 2 is equal to q2 upon epsilon naught. Due to q3, we require 2. So phi 3 is equal to q3 upon 2 epsilon naught. So that is the total flux. Phi 1 plus phi 2 plus phi 3. This will be the total flux. If there is a square plate, another example, if there is a square plate of side AA and there is a point charge, at a height a by 2 from the horizontal square plate Q. Now, what is the flux through this plate? So what we need to do is we need to enclose this charge. We need 5 more square plates so that the charge comes at the center of the cube. It will become a cube. So this is our Gaussian surface. And if we apply Gauss theorem, then we can say that phi net will be equal to q upon epsilon naught. And from each plate, so phi from the plate, there are 6 plates. So 1/6 of q by epsilon naught will be the answer. Let us take another examples. There is a cube There is a cube and infinite line charge is passing like this, having the charge density 3 lambda. Another infinite line charge is passing through this, having the charge density minus lambda, let us say. What is the flux through the cube? We are interested only in the charge enclosed. The length of the cube is, let us say, L. The side of the cube is L. So we can say this cube will enclose the charge. This charge enclosed will be equal to 3 lambda into L. Here, the charge enclosed by this line charge will be equal to minus lambda into L. So Q enclosed will be equal to 3 lambda L minus lambda into L. That is 2 lambda L. That is the charge enclosed, and phi net will be equal to Q enclosed by epsilon naught. It will be 2 lambda L by epsilon naught will be the answer. Let us say there is a uniformly charged ring having the radius r, and the charge density is, let us say, lambda, or we can say the total charge is q. So q is equal to lambda into 2 pi r. Ring is a one-dimensional body, so the total charge is this. There is another ring having the center on the periphery and like this. Here the charge on the ring is positive, let us say. What is this? Is our Gaussian surface. What is the flux through the surface? So the charge enclosed will be this only. We need to find out the flux. Now look, this distance will also be r. This will be r. The radius of both the rings are r. This is also r. It is an equilateral triangle. Another equilateral triangle can be drawn like this. This angle will be 60 degree. This angle will also be 60 degree. So from the unitary method, this angle will be 120 degree. So in 360 degree, the charge is q. That is equal to lambda into 2 pi r. So 1 degree for an arc making 1 degree angle, it will be q by 360. And for 120 degree angle, it is q by 360 into 120. That is q by 3 is the amount of charge enclosed. Or we can say 1 by 3 into lambda into 2 pi r. That is the charge enclosed. This will be the charge enclosed. Q enclosed will be this. Now, phi net will be equal to Q enclosed upon epsilon naught. So it will be Q upon 3 epsilon naught, or we can write it as lambda into 2 pi r upon 3 epsilon naught will be the flux through this. Now let us discuss a couple of questions from the JEE Advanced based on this concept. Look, if there is a cube of side A, this is, let us say, x direction, this is, let us say, y direction, and this is, let us say, z direction. The cube is placed like this, and E is given by E naught I cap, constant electric field, and the side of the cube is A. Now we need to find out the flux through this surface. We need to find out the flux through this surface. So phi will be equal to E dot A. E is constant, so A, or we can say EA cos theta. Theta is the angle between electric field and area vector. First of all, let us find out the area vector. This is A, this is A. So this will be root 2A, isn't it? And this is also A. So area will be given by root 2A into A. And the direction of area will be direction of area. What will be the direction of area? It is outward, like this. Electric field is like this. So this angle will be 45 degrees, isn't it? The angle between area vector and electric field vector. This is 45. So we can say it will be E naught is the magnitude of electric field into under root of 2 into A square into cos 45. So it will be E naught into root 2 A square into cos 45 is 1 by root 2. Root 2 will get cancelled out. So E naught into A square will be the flux through the given surface. Let us take one more example. This question was asked in JEE Advanced. Let us take another question. For a circular disk of radius r, there is a disk. If there is a circular disk of radius r, sigma is given by, the charge density will be given by sigma naught 1 minus r by r. The charge density. Now, the flux through the sphere enclosing this disk completely. The flux through the sphere enclosing this disk completely is equal to phi naught. And this is a sphere of same radius. It is phi naught. And the flux through the another spherical surface of radius r by 4. There is another spherical surface of radius r by 4, let us say, like this. This is r by 4. The flux through this disk will be phi. This spherical surface will be phi. We need to find out the ratio phi naught by phi will be what. So first of all, let us talk about phi naught. So the entire charge on the disk will be enclosed. So what is the total charge? For any small elemental ring dr, the charge enclosed dq will be equal to sigma into 2 pi r dr, isn't it? So for first part, charge enclosed will be equal to integration of sigma into 2 pi r into dr. The limit will be from 0 to r. Can we say phi is proportional to charge enclosed, because epsilon naught will have no role in that. Epsilon naught is constant. We need to find out the ratio, so epsilon naught will get cancelled out. So phi will be proportional to this. In the second case, q enclosed, the charge enclosed will be this part of the disk only. It will be integration again sigma into 2 pi r dr, but the integration limit of integration will be 0 to r by 4 here. So this is phi naught. So phi naught upon phi will be equal to integration of sigma into 2 pi r dr. The limit will be 0 to r divided by integration of from 0 to r by 4 sigma into 2 pi r dr will give us the result. So 2 pi getting cancelled out, and sigma is given by sigma naught 1 minus r by r. Sigma naught will also get cancelled out. So if we simplify this, our expression will be phi naught upon phi will be integration of 1 minus r by r into dr divided by 0 to r is the limit, divided by 1 minus r by r into dr, and the limits will be 0 to r by 4. It will be integration of dr will be r minus 1 by r into r square by 2. Put the limit 0 to r, then again 1 minus r square by 2, 0 to r by 4. This will be the limit. So that will give rise to r minus r square by 2r upon r by 4 minus r by 1 by 2r into 1 by 2r into r square, that is r square by 16. It will become this r getting as r minus r by 2 is r by 2 divided by r getting cancelled out. This r and r are getting cancelled out. R by 4 minus r by 32. Eight r minus r, 7 r upon 32. It will be r will get cancelled out. It will be we have committed some mistake now. 2 pi r dr. We have committed some mistake. The mistake is here it will be r dr. It will be r dr, sigma naught into 1 by r to r dr. This integration, we have committed the mistake. Look, our integration should have been like this. Our integration should have been like this. Phi naught upon phi is equal to integration of 1 minus r by r, r dr, 0 to r and 0 to r by 4, 1 minus r by r into r dr. This should have been our expression. So integration of r dr is r square by 2 minus r cube by 3r. Up the limit will be 0 to r, and here again r square by 2 minus r cube by 3r. The limit will be 0 to r by 4. That will give us the answer. So the first term will be r square by 2 minus r square by 3. This is the numerator. The denominator will be r square by 2. Sorry, it is r by 4. We need to put r by 4. We need to put in place of r by 4. So it is r square by 32 minus r square by 64 into 3, isn't it? So it is r square by 6. Denominator it will be 5 r square by 64 into 3. So it will be 1 by 6 into 64 into 3 by 5. So phi naught by phi will be 32 by 5. That will be our answer. This is how we can solve this question. I hope you understood this. So that is all from my side. Thank you. Enjoy. Take care. I will bring another session very soon. Till then, enjoy. Take care. Have a great day. Thank you and Jai Hind.